Okay, so today we're continuing to look at area under a curve through the rectangular approximation method. Now, I had said in previous lessons that area under curve, or this approximation method, doesn't always just give us the area under the curve, but rather it gives us distance. And the reason for that is because distance, you know from science class, is rate times time. Okay, and you're going to see in this example, it talks about an incoming tide, carries a bottle upstream, record the velocity of the flow of water every 5 minutes for an hour. So it's talking about time, and that's along the x-axis, and there's actually a table of data for this. And so that would be like the base of each rectangle that you're using to approximate the area under the curve. Well, that's the same as this time here. Now, the rate that it's talking about is the velocity. So this is like your y values that are given. Again, the table's not written here. I'm going to write it in a little bit, but I just want to give you that information. So if you look at the distance and you see it's two things being multiplied, and one's the base and one's the height of, well, if you were to draw out rectangles, then obviously this is area under a curve. Okay, so the distance that we need to find, because it says about how far upstream, okay, you may want to jot this problem down, implies we need to approximate the area under the curve to figure out this answer. Okay, so now that we established that, let me give you this table of values so you can write down into your notebooks. I'm going to stop this and it's just going to appear kind of out of nowhere. Okay, so write down this table. The table of values is important. I'm going to explain a few things about your table of values. Now, many times in the actual written problem, it'll describe your table. In this one, it doesn't describe all that much, but it is pointing out that the velocity is in minutes. That the values are going up every 5 minutes for an hour. So you can see that we go from 0 to 60, so that is an hour in minutes. And so you can see that they are going up by 5 minutes. So that's a subinterval. You're going to see that there are 12 subintervals if you keep counting between like the 5 and 10, the 10 and 15, the 15 and 20, even like the 30 to 35, the 50 to 60. 55 to 60. I got ahead of myself. There are indeed 12 subintervals. All right, that's the point there. I just erased the 1 in my 10. I'm sorry about that. As you're writing this, hopefully you write the right number there. And this is supposed to be an 8. It did not come very well on my iPad. This is 2.0. This is 1.8. All right. So another thing that I'm going to point out that we should see in the table is that the time is indeed measured in minutes, but the velocity is measured in meters per second. So even though they have the same length of 5, what I would do is change the length into seconds so that it complements the velocity that's measured in meters per second, okay? So 5 minutes is actually 300 seconds. That's going to come into play when we have to answer part A and part B. So in part A, we're using the method of the left endpoint to find out how far that bottle went upstream. So we're actually finding the distance using this format. It's an approximation still. And you can imagine that there's rectangles built in. You don't need to graph it out. And each rectangle would have the same base. And it's not the 5 minutes, but into the 300 seconds. Now, the left endpoint would be using the first value here, not that 0 at the end. So you can write out some of these values if given. Okay, show what you're starting with and what you're ending with. You're not ending with the 0, so this is the correct approximation for part A. So it turns out to be about 5,220 meters. Okay, it's the distance, so remember your units. It's not going to be in meters per second. It's not going to be minutes either. That M is for meters. Okay, so for B, the distance be approximately, again, you can take out the 300. If there was a change in measurement, let's say that went from 0 to 6, and then 6 to 10, and then 10 to 15, then you have to do the multiplication for each one, like base times height plus base times height plus base times height. If you didn't get the table down, you should have. I'm more concerned with you now getting down this work. And let me know if you have any questions as to what I'm doing to find the distance. All right, so we're up to part B. In our RAM, we're using the right endpoint. So that means that we're starting from here and we're going to 0. So it would be established like this. Again, you can only use these ellipses if you have the data written. If you don't, I don't know where it comes from. And you need to have at least 3 values, the beginning and the end. And there we have it. So by using the right endpoint, okay, we can calculate that the distance is approximately 4,920 meters. Okay. So looking about that, they make sense. They're not far off. I would say that bottle went about 5,000 meters. So if you're getting numbers that are really far off, that should not occur because these values for y are not very far off. So let's look at another problem. Okay. So this formula was given in pre-calc and explains a little bit. I may have done it in previous calculus classes. So, lessons. Let's say you have a function and you're drawing in your rectangles. Okay, we particularly like using the right endpoint and for our formula here. And the reason for that is because your base refers to like your x values. So let's say this is x equals a. We're going to start drawing our rectangles. That's your x-axis. Height. So right endpoint is more useful because it kind of finishes your rectangle. Going from this x value, you just started drawing a rectangle, but over here, it's supposed to be an arrow, you finish drawing that first rectangle, so I would be 1. Now you know in math that if that's I, then before that the notation would be, I'm running out of room, minus 1 because it would be before. Okay, so we don't like using the I minus 1 reference here because then it becomes a more complex expression that needs to be plugged into our function. So hopefully you can understand that. Okay, so we don't like to use LRAM. Instead, we like to use the RAM formula. Now, this is actually saying the same thing as RAM. It's just establishing it in a formula. So in finding our rectangular approximation method, we have base times height. Actually, that's your base, that's your height. Your height's determined by your function. So we're plugging something in to the function to get the height of our rectangle, because let me draw this again. Our height of a rectangle is based off of this right endpoint, so you can see it's on the function. So this expression is the height, this expression is the base. So we're going to do this example now. With the example, it's very much like problems we have done in pre-calc, so I'm going to go over the rules of summations that are necessary to use for summations, okay? All right, so let's get going. Okay, so we're going to rewrite this summation. I is 1, that's for your first count of your rectangle, and there's supposed to be 4 rectangles in our example. That's the only time you actually substitute the number 4 is here. So now we have our function of something. Luckily, a is 0, and b minus a over n we actually want to keep in terms of n. So it would be 5 minus 0 over n times I. We're going to come back to this. So we just want 5 over n for our width. Okay, I showed it here, I simplified it there, so that's okay. You show it once, the full substitution. So now, sometimes I like to just take out the 5 over n. N is a certain number of rectangles. We happen to know for this problem is 4. In later problems, we don't know the exact value. So I'm teaching it to you where we don't know that it's 4. So we can take it out in front. You don't have to, you can keep it there. Your upper and lower indexes are always the same for summations. So now, let's see what we're using here. This is f of 5i over n. So that means we need to plug in to our function wherever we see x of 5i over n. Luckily, it's just x squared. Please be careful, as the more x's, there's more substitution, okay? So now this actually comes out to be 25i squared over n squared. For some reason, that looked like an h or a 4 or some number. It's an n, and this is an n. So we're treating this as a constant, so I'm going to also pull that out in front, and they get multiplied together. So 25 times 5 is 125. N squared times n is n cubed. Again, this may be familiar from pre-calc. So we get the summation of, actually I'm using I, not j. Sometimes it's a j. I jumped ahead. So of j squared. It's just the summation of I squared. You need to keep your variables to the right and only move the constants to the left. If you move a variable to the left, then you did it all wrong. It's all messed up. So please be careful. So now, so I'm just going to write what we got in our last step. And that way we can kind of continue from there. So there are formulas that we learned in pre-calculus, the sums of powers of integers that would help us here. So if you don't remember them, I do advise that you review and go over what those formulas are. And there's larger fractions to memorize or smaller ones. I'm going to use the smaller one here. So the summation of j squared. I'm going to actually leave this, I'm going to change this a little, in terms of n, because the formula is going to stay in terms of n from 1 to n. So it's n cubed over 3. Okay, so let me finish this formula. N squared over 2 plus n over 6, and I don't know why I'm changing colors. Now the 125 over n cubed stays on the outside. Now, what we can do is simplify this a little bit, and that helps us later on when we have to do limits. Okay, as far as this particular problem. So we're keeping where n is equal to 4. So I'm going to substitute 4 into our expression here. And let's see what we get. So I'm going to use the calculator to do so. So I'm getting that the area is approximately 58.59. I'm going to round to 3 decimal places, so that would make that a 4. And this is the approximate area that I get in square units. So let me know if you have a different answer. And that's that.